This presentation was recorded for students participating in EPO 322 Diesel Engineering 2 simulation at the California Maritime Academy. It is presentation 9 and it covers motor vessel heavy fuel oil service systems. Alright, here we have a modern slow-speed diesel. This particular one is the RTA 84C 840 millimeter bore Wärtsilä slow-speed engine. Regardless of whether you're Burmeister Wain or the Wärtsilä, these slow-speed two-cycle crosshead engines are the backbone of the industry. Primarily because they can burn heavy fuel oil with the lowest maintenance rates and can burn it very, very efficiently and cleanly. Medium speeds, though, they are able certainly to burn the heavy fuel oil. They have slightly more costs associated with this. And so these big slow speeds can be said that their fate may be very well tied into the heavy fuel oil availability. If heavy fuel oil was to go away, there is an argument that these ships might, these particular crosshead engines might disappear. Again, the medium speed engines to sell in today's market will have to be able to burn heavy fuel oil effectively. This particular one is a Burmeister Wain. It is mechanical fuel injection. When you look at on the on this side of the engine, that's your fuel cam, right, with your high pressure pump above it. One thing that's interesting too is look at the slope of the cam. You can see that that really accelerates the pump plunger very quickly. But you notice I've got fuel cams on one side, and over here on this side I have my exhaust and my intake valves. The reason for this is variable injection timing. This is a mechanical system, but the reason they have on a different camshaft for the fuel pumps than for your exhaust and intake valves is specifically so that I can make adjustments to this camshaft on the fuel pump side, even when the engine's running, to be able to give me variable injection timing and deal with the ignition delay that can occur with burning heavy fuel oil. Now, the reminder is on this that what is important for a diesel engine is the viscosity at the tip. Even if your viscosity in the system is correct, if it is not correct at the tip, you will not get proper combustion and proper atomization leading to proper combustion. So it is essential on a heavy fuel oil ship, or any diesel for that matter, that the viscosity is correct at the tip. Now, this can be a problem with heavy fuel oil. And as a reminder, some of the heavy fuel oils today at room temperature can go to an absolute rock hard solid. So it's very important that for a heavy fuel oil that it's heated properly and its viscosity is controlled through heat. Now, on this diagram, this Seconds Sable Universal, Seconds Redwood are older standards that have fallen away. These are viscosity standards. Today you're going to use the millimeters squared. This is the centistokes. And this scale goes all the way from 0 up into an ungodly amount like 100,000 centistokes. Now down here, and this is for a Sulzer RTA, but most diesels burning heavy fuel oil will fall into this range. They're showing about 13 to about 17 centistokes. This gray range right here, when you're burning heavy fuel oil, that is the range that you have to be in to burn the oil. If you go thicker, which is going up, it becomes thicker. If I go above, say, 17 centistokes, You could get improper atomization on heavy fuel oil, and that could cause the engine to stall or stop. If you go below this, then you lose lubricity. The lubricity of the fuel oil is the ability to lubricate the pump plunger. Now, if you get too thin, what ends up happening is excessive wear or even seizure of the pump plunger in the barrel of the high pressure pump due to insufficient lubrication. So I've got viscosity on one side. Whoops, excuse me. I've got viscosity on one side, and then I've got temperature down here. And the upper one is degrees C, and if you need a comparison, Fahrenheit's on the bottom. And we have three fuels we're looking at: marine gas oil, marine diesel oil, and all of these lines are typical viscosity grades of heavy fuel oil. So first off, let's talk about the distillates. Let's talk about marine diesel oil. Now, at 50 degrees C, it is 0 centistokes. Right, at 50 degrees C. And these can be at different temperatures as far as when they're taken. But I believe this one is at 60 C. So anyway, marine gas oil is number 2 diesel. It is the same grade that you would get at the pumps in any place in the United States. So it is a distillate. And it is a fairly light oil. Its properties are very, very highly regulated. It has a cetane number, which the cetane number will substantially control ignition delay. On these, if I remember right, the ignition delay with 32 centistokes is about 10 milliseconds. So very reliably, that when injected, that fuel will atomize and have a very, very reliable ignition delay. Whereas when you get into the grades such as marine diesel oil, MDO, or HFO specifically, their ignition delay can vary radically, and they have to have, on a modern engine, you have to have variable injection timing, whether you're mechanical or electronic, to be able to control that ignition delay, or you'll get a very, very rough engine that's going to start stalling on you. Now, one of the things that you have to think about too is we are dealing with two different, three fuels, but these two are distillates and these are heavy. So these are distilled, right? They're distilled from crude oil. This is the residual from heavy fuel oil after the cracking process. Very different fuels with very different properties. So when you're talking about doing a fuel oil changeover from HFO to distillate or vice versa, what you have to understand is you are dealing with substantially completely different fuels. Now, let's talk about MGO. And unfortunately, right now, to meet the regulations for California, and this is equalizing with ECA, environmentally controlled areas, where 2015 it equalized all North America. Is basically the ECA rules have merged and are pretty much equal with California. You're going to have to switch over 200 miles out from heavy fuel oil or over to a clean low sulfur distillate. The loophole on this, by the way, is you can put in a scrubber, and unfortunately some of the companies really are considering this, where you would scrub the sulfur out of the flue gas, and then directly, instead of putting it into the atmosphere and waiting for it to form acid rain, you just dump all this acid straight into the ocean. But that's another subject. So let's look at marine diesel oil. Now, on lubricity, marine diesel, MGO, marine gas oil, you cannot be below 2 centistokes. If you go below 2 centistokes, you're going to have trouble losing its lubricity, and you'll have excessive wear on the pump plungers and possibly seizure. Now look, I'm starting at 50 degrees C. This is actually a problem, and it does vary a little bit on this. But at 50 degrees C, that's actually a normal fuel temperature to most of these engines. You have a recirculation type of fuel system. You're circulating that oil through the engine itself, and the engine typically jacket water temperature is about 80 C. So one of the problems we're having is it getting, particularly with marine gas oil, is that it's getting too thin and you're getting excessive wear on the pump plungers. Now, on this, some plants, some ships are actually putting in a cooler in their fuel system. Besides the heater, now you have a cooler so that when you're running marine gas oil, you can actually chill it and get its viscosity up. Because take a look at this, from 50 C, if we follow this all the way up and it's off the chart and it's still not at the minimal that what heavy would be, right? Or let's talk about where we would get too thick. We're already about, say, a minus 20 degrees Fahrenheit or down pretty close to 0 Celsius. You're not going to operate like that. You're not going to have fuel in your tank. So we're never worried about this getting too thick. We're just worried about it getting too thin. Marine diesel oil, and this is a common but not absolute. You would, on this, you wouldn't worry until it got about too cold and started getting too thick to somewhere around about 11 degrees C or 50 degrees Fahrenheit. Again, that's really not an issue. So what I'm doing to get the viscosity up on this where I'd want to be, is let's talk about, again, this is not usually a problem with diesel oil. Let me switch over to heavy. This one is 50 centistokes up to 700 centistokes. Typical one that we burn on a ship is about 380. So let's pick that off. You see the 380 there. We're going to follow this down, right? We're going to follow this line down until I'm in the middle of my viscosity range, and then I'm going to follow this line down about 140 degrees C for 700 centistokes. The simulator uses 120, so that's probably going to be somewhere around a 180 fuel or 240 centistokes. But again, that's all you do to use this chart, is whatever fuel you have. If I have 380, right, I'm going to follow this down again until I'm in the middle of the range, and then follow that down, and I'll burn that at 140 degrees C. I've seen fuels, unfortunately, up to 160 degrees fuel with these 700 centistokes. Okay. So this is a problem here. Take a look at the temperature. We're talking somewhere between 240 and 300 or 320 degrees Fahrenheit. So very, very high temperatures to be able to get that fuel thin enough to atomize and burn. Measurement of viscosity. On the simulator, I picked this one. This is not one of my favorites, but it does work. And again, it's the one on the simulator. I have a constant speed gear pump. So running at a constant speed and having a standard mesh between those gears, it's going to pull in fuel from the fuel inlet and give you a very reliable volume output that I'm putting through this capillary tube. Now, what's going to happen, the thicker the fuel, the higher the pressure to equal that volume. And what the viscosity scale is literally a differential pressure transmitter, but instead of pressure, it's been calibrated to read off in viscosity, because a heavier fuel will increase that pressure, right? The pressure differential to try to get the volume through this capillary tube. So this is an older system that you would have seen around in the, say, in the 1980s. In this particular era, we were burning about, at max, about 380 centistoke fuel. You had a mixing tank. The mixing tank is probably somewhere around a 10 or 15 inch piece of pipe, about 10 foot high. It's a volume chamber. Now, one thing I want you to notice is your ship's service tank. level of the top of the day tank, level at the bottom of the day tank. So off to the side here, our tank would be in that range, and we're gravity feed into the mixing tank, right? So it's gravity feed into the mixing tank, and what they're saying is your mixing tank would have to be between these 2 points to properly gravity feed. So it's feeding that in, and then we're going into a suction strainer, booster pumps, heater, self-cleaning discharge strainer, and then into the suction galleries of your pumps. And when the engine is shut down, specifically, all of that fuel has to go through this regulating valve, through a viscometer, and back. So with the engine shut down, this fuel is going to circulate like this, right? It's going to be continuous circulation back to that mixing tank. The reason for this volume chamber is that with viscosity, it makes it easier to control, because I'm going to control viscosity with these heaters, and I'm increasing the heat of this larger volume of fuel will make it more stable. Now, with the engine shut down, though, there is no recirculation on this older system. So there's no circulation from the high pressure pump to the injector when the engine's shut down. And this is some concern, and that's why you weren't using over 380 centistone. Because of the viscosity of these fuels, as you increase the viscosity, you increase the possibility of having a problem. Now, these high pressure pipes, around them had a steam tracing line to keep the line hot when it's shut down, and then typically the injectors themselves had a injector cooling water system, and prior to getting underway and running at slow speeds, or when the engine shut down, you're actually going to heat that injector cooling water to keep the viscosity in the tip thin enough for injection. If you forget to heat up prior to getting underway, the engine probably won't start. So now let's switch to it. Okay, the engine started up, and we're running, and we're moved up to maximum continuous rating. We're burning the maximum amount of fuel that that engine would normally consume. So that fuel's going to be pulled in, again, go through the system. It's going to go into the pumps, and it's going to go to the injector. But what I want you to understand is, with this recirculating valve, this booster pump is typically around twice the amount of fuel delivery that the engine actually needs to run out at maximum continuous rating, MCR. So even when this engine is at full load, you're going to have as much oil returning back to the system as that you're actually burning. So it's going to go this way, right? Part of it. And then the other part of it is actually going to go into the pumps and be injected into the engine. By doing that, I know that the viscosity as the tip is going to be the same as the viscosity in the line. And by having this large volume chamber and continually recirculating the fuel, then I can be assured that I won't have, that I can maintain the viscosity at the proper rate. Okay. This would be on this is an old R&D, or excuse me, the RLB engine. Here's your high pressure pump, and you can see the length of your high pressure line, and here's your injector again. And again, there would be steam tracing all around this high pressure pipe, and your injecting cooling water system would keep this hot. They had, these were a loop scavenged engine, and they had one big old, about a 300-pound injector sitting right in the center of this. So on these particular engines, they had a passageway that would go all the way down to the tip here, right, to lift the needle valve for injection. You'd get a pressure wave going down, working on that angle to snap it open. But there was another passageway that would come down, go around the back side of the, or actually on these it would come down around here and actually go back up with the leak off. So this is your high pressure line coming in, and then these are those two passageways going down to the injector needle valve, excuse me, injector needle valve, or fuel valve for the Europeans. This would have been your injecting cooling water system here, going into and then back. And then this was a purge valve. Now, one of the things about a non-recirculating type system, and what is funny today, with these older ones, they were non-recirculating. Burmeister Wayne has circulating type of injectors today. Wärtsilä, on some of their engines, it's recirculating, and some of their engines, it's not recirculating. For an operator, this is kind of an important thing to understand and know about, because one of the things, let's say I pull, right, I go ahead and I pull this injector. I go ahead and pull this injector out and I replace it. When I put it in, these passageways are all going to be filled with air. The problem with that is when I go to roll this engine over and this injector has air in it, what's going to happen is, being airbound, you're not going to get proper injection. This is a hydraulic system, and you can't have air in a hydraulic system and operate properly. It's like getting air in your brakes. If you leak on your automotive brakes, if you have air leaking in, when you try to apply the brakes, your foot's going to go all the way down to the floor, and you're not going to get any braking force. This is the same thing. So what they had here was a purge valve. And what happens, you take a crescent wrench and you back this off, this pulls down, and this is a little ball check valve. So you have system pressure from the booster pump coming up through the high pressure pump up here. When you open that up, then it can go down this way, and then the front of the cylinder, there was a little cup, and that line would drain into that cup, and you would open up this purge valve and you'd watch and you'd see it sputter with air, and all of a sudden you'd get a solid stream. As soon as you get a solid stream, then you can go ahead and close this off and you've purged it. The other one on here, this, by the way, is your leak off. Now typically what that's going to be is you have to have some lubrication of the needle valve and the bushings for this spindle, right, has to be lubricated with fuel. So some you will have a minimal amount of leakage past this way, and then that comes up and that's your leak off. So the same thing would drain into the cup, and you'd probably see a drip every 15 or 20 seconds for a normal operation. So let's talk recirculation style fuel injection system. This is a Wärtsilä. Now, in this particular one, this would be my diesel oil service tank. This would be my heavy fuel oil service tank. And then this would be my settling tank. So my purifiers would take a suction from the settling tank and pump that fuel into the service tank. Now on this, you notice all this symbols right here. That's the symbology for steam tracing. So on heavy fuel oil lines, all of these have steam tracing on it, right? So that oil in the lines will stay hot and will not solidify or get too thick to pump. Typically, most common heavy fuel oils, you will not be able to even pump it unless it is above 40 C. It will not pump. The other thing you'll notice is everything has steam tracing on, not just the lines. All right, so you notice this one, what's been added is I've got another set of pumps. Typically, these are going to be called supply or service pumps. They're taking a suction off the heavy fuel oil tank through this three-way mixing valve, and then through the pump and into the system. Right? Then this is a small mixing tank, and the mixing tank anymore, it was actually in many cases have been removed. We'll talk about that in a second. It goes through a circulating pump, circulating or booster, either one, through a heater, through a viscometer here, and here's your filter. Then it goes into the pumps. By the way, number 34, these right here, those are your accumulators. Now it goes through a circulating valve also, which is coming up here and back, and I believe this 31A was a circulating valve. Now, what that's doing, again, at when the engine is shut down, this is going to be wide open, and all of the fuel is going to come up, like I said, go to the pump, come through here, and be recirculated back to the suction. So all of the fuel is going to do this, right? Now, as soon as the engine starts, some of that fuel is going to be injected into the engine. And as more and more fuel is being delivered to the engine, the pressure would tend to drop. This will close down to maintain the suction pressure into the pumps the same, and the volume of fuel going back to the system would drop down. You also have a valve here where I wished I could close this valve and open this valve, so I would take a suction off the day tank and pump it into the service tank. Absolutely not recommended unless it's an utter emergency. For one thing, think about the bear. Think about where your fuel oil service tanks are, and think about whether you'd want to heat that up to 250 degrees Fahrenheit, right? You want this, the whole purpose of this circulating system is when I heat up the fuel to a high temperature, I'm minimizing the amount of fuel that's affected by this, and I'm keeping it in a closed loop. Your tanks are typically heated up to a much lesser extent, usually about 60 to maybe 80 degrees C, yet this system is up at 120 degrees C. And there's specific reasons for this. The one that is one reason that you would use this valve is, let's say the main engine's been shut down and I want to be able to change over. Well, even if I open this up to distillate, the fuel is going to go through the service pump and try to go into here. But if I'm just circulating and I'm not burning any fuel off, there's no way for that fuel to come into the system. So instead, this regulating valve number 31 opens and the fuel just goes in a circle like this, right? That is going to control. So if the system is full, if the circ system is full, none of the fuel is going to go in. There's not going to be any flow through the flow meter. Instead, it's going to recirculate back to the suction of the pump. So when the engine's shut down, this pump is just circulating. Well, on this side, these circulating pumps again are going around like this. So if I want to change over, just changing this, that diesel comes down, all it's going to do is just go in a loop. It's not going to get into this system. So what I would do is open this again and close this. It's going to take a suction off the distillate tank, or off your distillate service tank, MDO tank. It's going to go push that oil through the system, and it's going to return it back to the MDO, the heavy fuel oil service tank. There's a problem with this. Now, I can remove the heavy fuel out of here by doing that, but I've just taken oil, distillate, and I've mixed it into my heavy. That causes a problem right there because they're worried about incompatibility. And with incompatibility, if you mix the two fuels, you could actually have sludge building up in the bottom of this tank. And I've heard as much as 8 feet, which actually would clog off the suction. So you would never want to do this unless it's an absolute emergency and you had no choice. Let's say the engine's shut down, you're out at sea, you've lost all heat, the main engine's shut down, you can't light off on HFO because something's wrong with your boiler. So what you could do is you could take and open this valve and close this one as I've described, and you could blow that oil into the HFO tank until you get the viscosity down in range, and then you could switch this back and start the engine up. But you might find the mistake is that you might be down again fairly shortly because the sludge buildup from incompatibility in this tanks can actually block off your suction, and you'd lose suction on the HFO. You switch back to MDO because that's your only choice at that point. And typically most ships only have a very, very limited supply of MDO. So the whole point of this design is when they design this, where I'm heating this fuel up to these very high temperatures, it's circulating in a loop, and we're limiting the exposure to this high heat. This happened when they went from 380 centistoke limit on the fuel to 700 centistoke. During the 1970s, during the oil embargo, they wanted to be able to increase or burn a much lower quality fuel, but they'd have to heat it up much more, and they've added, again, these extra pumps because what they're worried about is the circ pumps take a suction from this mixing tank. That's a low pressure area, and with these very high temperatures, it's going to flash into a gas and cause cavitation of the pumps. The other thing is this tank is vented, and you're going to get much more gaseous discharge out your vents, and you're going to be degrading that fuel. If I was to heat this tank up to 120, all I'm doing is I'm continuously venting the lighter ends off into the atmosphere, making this heavier and heavier and heavier. So, to cap up, the service pumps are there to supply into this system and maintain the oil at the suction at the pump at least 5 bars. Typically, the booster pumps or circ pumps are going to boost it up from about 5 bar to about 7.5 to 9 bar to supply the main engine. I have accumulators that are there on this particular Wärtsilä brand. The way they do this is to reduce the amount of pulsations in the line from whenever the high pressure pumps end their effective stroke, they dump high pressure oil back into the suction of the pump. And this is to minimize those disruptions and spikes and prevent damage to the piping. This is your heater, and you control viscosity through heat. And sometimes you will also, now on the plants, they will put on a chiller. So when you are on light distillates, you can also control viscosity with temperature by reducing the temperature to increase the viscosity. Visciometer. Now, one thing while I'm here too on the visciometers, typically on a ship, visciometers fail on you. So when the ship is operating well, you've got a good visciometer, keep an eye on your temperature so that if the visciometer fails, there will also be a temperature regulator there, and you need to be able to run down and set that temperature for the viscosity that you have. And again, if you are keeping track of that and know what the normal temperature is, you've got a starting point. Now, let's talk recirculation at the injector. These particular systems have a recirculating type for the injection where it can, when the engine is shut down, not when it's running, when the engine is shut down, fuel will go up to the high pressure pipe to the injector, down to the tip of the injector, and then can return back to the system. Right? So with the engine shut down, there is a continuous flow of, a small flow of oil into the pump, through the pump, up the high pressure line, down to the injector, down to the injector tip, and then it returns back to the system this way. That way, by circulating this, I can automatically purge any air out of the injector. If I pull an injector out for service, I don't, on these ships, have to worry about purging it. The circulation will purge it, air automatically. It will also circulate oil down to the tip to maintain and have good assurance that the oil at the tip will be the same as in the system when the engine is shut down. When the engine's operational, that recirc function is totally shut off at the tip. because that would be disadvantaged. That would mean that that pressure pulse would get dissipated. So this is just that RTA engine that we were discussing the system. And these are, whoops, these are the high pressure pumps here, and the injectors would be up at the heads of the covers. These fuel injection valves are located, there's usually 3, located around the exhaust valve. This is the high pressure pump. This is the same pump that we talked about in mechanical fuel injection, the Wärtsilä pump, the old was originally Sulzer. The fuel comes in, and this comes in from the circ pump here, can actually go in, can go up through the suction valve, through the delivery valve, up. In these particular one, they have a distributor that splits it, through the circulation valve down to the tip, and then back to the system. Right? So with the engine shut down, I have a continuous stream of oil through the high pressure pump, high pressure lines, down to the injector tip, and then back. And then down here, here is your recirculating valve, so I will also have oil flowing into the pump, into the suction gallery, and back to the system disk direction. A much higher volume. This is a fairly small volume. Now, how this works, we don't have to get overly complicated this, but what I'll point out is this is your circulation valve, and it is screwed into the, pretty much otherwise standard injector. So this piece right here is the same as this piece right there. And this is the oil would come down, the oil would come down, go right to a needle valve, lift the needle valve, and injection would occur just like it used to. Now, these two are to show you the internals in 2 different states. It has an internal needle valve that's hollow, right? There's a passage that's been drilled down, and then on this angle here, there's small holes that are drilled through. And this has 2 passageways, one directly below the seat, and then there's another one. There's little holes around this outside of this needle valve, and the oil can go down this way, down here, and down to the back side of the tip. But that's what they're showing here. This and this at the same time. This you're looking at it from the side, this you're looking at it from the top. It can go around the tip, right? So it comes down, goes around the tip, up and back with your circulation. This occurs at about, and by the way too, this is a spring. This occurs when the engine's shut down. You're only going to see, in this case, 7 bar. That 7 bar acting on this shoulder is not enough force to lift the needle valve up against this spring. So the injection port is closed, and the recirculation port is open, which is actually the port is right up here. Once the engine rolls over, that injection pressure is going to jump from 7 bar to 1,000 bars. That's a big pressure drop. Comes down, it lifts this needle valve off its seat. That closes off, absolutely closes off the recirculation, and the oil goes down this passageway right down to your main injection needle valve, lifts the needle valve, and injection occurs. So basically what this circulation valve does, it is a needle valve being opposed by a spring, and it has 2 states. In one state, it is when the pressure coming up is low and the engine is shut down. You've got circulation taking place. When the engine rolls over and I have 1,000 bar oil coming in, then it goes down to the needle valve and injection occurs. So this is the way Wärtsilä did this. Burmeister Wain is actually very similar, but instead of it being a separate valve on top, this needle valve was buried down in the body of the injector. So you really had like a needle valve and a needle valve. This is the newest system that Wärtsilä has gone to, and this has actually been somewhat of an advantage for the changeover for them. But in this case now, this is like this is really a non-recirculation system. What happens now is it can come in, go in, right, and through the suction valve again. And then this fuel distributor is just breaking up into the stream into 3 equal flows, 1 to each injector. And so that oil comes up and into a standard MORV injector. There is no recirculation function here. What you do have is on these is you have a supply circulating pipe. You have fuel oil coming up and then into the injector down near the tip, then back, and then down and back and down. And then you notice they're actually keeping that fuel distribution block hot and then return back to the system. This is actually very similar to the one I discussed previously for that injecting cooling water system. They've changed the cooling passageways in the head. You don't need to cool the add a cooling water to keep the injectors from burning anyway. But like this, now what they're doing is they're actually using the hot fuel. They're using the hot fuel circulating through the injectors continuously to make sure that the injector stays hot and this fuel distributor block stays hot. The advantage to this, when you switch over to distillates, you can shut this off so that your fuel is not going to pick up heat, right? It's not going to pick up heat in this system anymore. When this engine shut down, there is no circulation going into the injectors, so you're just heating them. So with this type of system, by the way, if you change out of injector, you have to purge it again. This is just what the injectors look like, and right here, this is that piece I was talking about. That's your circulation valve, and then this is all the injector itself. It's got kind of a rectangular top to it and a round body, and that's the actual tips down here. So this is the Burmeister-Wain system that is on the simulator. Right? This type of system they call a uni system. With the uni system, what they mean by that is a heavy fuel oil system for the generators, and the main engine is the same. And you notice there is no mixing tank on this. They have this up here is called a vent box, and it's just any gasification, any gases that accumulate on here would be vented off. Right? This is a standard Burmeister-Wain system that they supply these drawings to the shipyard to when they are designing the vessels. This is the simulator fuel system, and this is very, very similar. This is your main fuel system. Let's actually pop one down. Now with this is coming from my diesel oil service tank, heavy fuel oil service tank, and they feed into a 3-way mixing valve that I can change the position. Here's my 2 supply pumps, and with the simulator running, if the engine shut down, what you'll see is a lot amount of the fuel just circulating, and you can see the flow rate down here. Then we go in through a meter, fuel oil meter. This freshwater emulsion control, this is if you want to reduce NOx. It would emulsify water with the incoming fuel to give you a NOx reduction and act as the coolant. Into my circulation pumps, then we go into one of the heaters, right? And then into your back flushing filter. Here's your viscometer, and then there's your recirculation valve. Oh, excuse me, that's the solenoid valve. That is for an emergency shutdown of the engine, and it actually comes off the emergency board, This is your recirc valve, sorry about that. And then recirc back through the venting rod. There is no mixing tank in this, which means there's much less fluid in the system, which means it's going to make it a little bit more difficult for you to change over. But also off of this system is this goes up to your diesel generators, and your generators, it circs up to the generators and then it returns back. Right? Now, typically with this, I would never have this set up to go back to return to the service tank. It would always go back to the suction of the pump. Fuel leakage detector. If you have any leakage in your high pressure pipes, there will be a float in here, and that fuel leakage would go into this space, start to fill up, lift the float, and sound an alarm. So this fuel leakage detector, what you're really looking for is leaking high pressure lines. You have a solenoid valve for an emergency shutdown of the main engine that would shut off fuel to the main engine. The back flushing filter. The good thing about this back flushing filter is that it's actually usually Bull and Koch is the manufacturer of these. They have multiple candles. All right. The other one, just briefly on the viscosity, and I talk about this quite a bit in length, I think, on the PTT videos. So I'm just going to briefly do it here. The viscometer feeds into this controller the actual viscosity of the fuel. And then we would put a set point in here. And depending upon whether the fuel is actually above or below the set point, that is going to send a signal down to a temperature controller. And that temperature controller is looking at the temperature of the steam chest in these cases actually, and the temperature of the fuel. This is called a cascade system. When the viscosity changes, what this is doing is changing the set point of this temperature controller. The viscometer goes bad. This is where you would go to and where you would put in your set point to control the temperature if the viscometer had quit on you. Again, this is on here. It's a separate. It comes off the main fuel system, goes to the generators, and comes back again. These are your main engine high pressure pump system. You have the puncture valve when air signal can shut down delivery. You also have your variable injection timing system, right? And here's your fuel rack and your shock absorbers. So this is a ball and Koch filter. Each one, typically only one of these candles would be on at a given time. And here's your indicator for your pressure drop, right? Pressure differential across that filter. Let's say we're on this filter right now, and this starts to go red. When it gets pretty much full red, the pressure differential will cause this motor to start up through its control system, and it will actually shift from this dirty strainer to a clean one. So it will automatically switch to a clean strainer and then automatically put air to backflush this tank down the sludge down into a slop tank right below the unit. Keep an eye on these. This is important to realize that your purifiers, if they're not set up properly, can actually, particles can go through the purifier, not be caught, and go to the main engine. And you're really worried about things like catalytic fines and that type of thing. So there is a lot of worry that you can take, and if your purifiers are not set up properly, that you could have catalytic fines going to your engine and not being stopped. This is your last line of defense. So if this is plugging up more than usual, you may have a problem with your purifiers. Now what happens is every time that these chug to a new clean strainer, that's recorded, and it's usually in the motor controller for this unit that controls this motor up here. And watch the counter so that you know on a normal basis how often this shifts. If it starts shifting a lot more, then you may have a problem with your purifiers. You also want to look at the sludge from this on occasion to see what's coming out. What kind of material is it removing? If the purifier system was perfect, we wouldn't be catching anything in this strainer. So keep an eye on it. The other thing that will happen to you, though, is if you allow, like startup of the system, if you're just starting the system up, where it's got a lot of viscosity, it's pretty thick, this will start chugging through just because it's reacting to the pressure drop because of that viscid fluid, and you will get an alarm because it's rapidly changing filters. And then you will have a final filter that's with these, that is your final line of defense, a very fine filter to prevent material getting into the engine. So let's talk about now the Burmeister-Wain system. And here is their fuel pump, and then it's going, going up to the injectors in this area. Their fuel pump has the puncture valve so that a pneumatic air signal can eliminate fuel delivery. And here is your suction valve. This is a little bit different on this as far as some of the other drawings. And then here is your shock absorber so that whenever you end its effective stroke and you're dumping that high pressure pulse down, that this will take that pulse. And then again, you have a variable injection timing plus your standard fuel rack. And this is what the pump looks like. This little line right up there, that's to activate the puncture valve. These are the high pressure pipes going to the injector. There's usually two off the same pump. These wire braid again, if you were to get leakage or bursting of the high pressure pipe, that's to shield it from spraying into the engine room and causing a fire. And that oil would drain down to a tank where you would get an alarm that you have leakage of the main fuel lines. This is your shock absorber. And these are actually drains that would drain off any leakage within the interior of the pump. This is the Burmeister-Wain circulating, and it's got a needle valve up here for circulation or no recirculation, and another needle valve down below that controls injection. So what they're showing in circulation, again, I have like 7 bar, and that oil will actually go through a passageway, and they're actually kind of showing it to you over here, but it goes back again with the leak off. When the engine turns over and the pressure in this dramatically raises, this pops up and the fuel can go through. The recirculation is shut off, and where they were showing you this is right in here. This becomes closed and the oil can go right down to the tip and injection occurs. So very similar to that Watt-Cylinder. And again, these slide valves now are the norm because they have no sac volume. And this is more of a spool valve, and the fuel comes down, lines up with a hole and shoots out, and as soon as that spool moves, it shuts off the hole. But these have a circulation inside the body of them. There's some good pictures of it. And this is actually here where you can see that it's more of a spool valve now. That oil comes down through this hollow, and then it can inject through the tips. And when this moves up and down, it closes the injection holes. Alright, I'm going to pop back up and talk about the changeover process here real quick. When you change over from heavy distillates to light distillates or vice versa, there's a couple things that you have to look at. One of them is the injector tip itself and the fuel pump. You're going from, you're burning heavy fuel oil at 120 degrees C and you want to switch over to a clean distillate that you want to be down at about 40 degrees C. When you look at the viscometer here, the range is between 12 and 16. That's heavy fuel oil only. If it gets below 12, then it's heavy fuel oil will lose its lubricity. If it gets above 16, then it's not going to atomize properly. With clean distillates, it's no longer 12, it is 2. And you're never really worried about it getting too thick. So when you're changing over this fuel, and in the simulation, we're changing over from clean distillate typically in the system, because shutting down this engine, what you would typically want when you, prior to shutting down, you'd want to change over so that the system is full of distillate when you're going into a shipyard. And that's what we're supposing we're coming out of a shipyard. So typically this would be full of distillate. Well, in this scenario, for scenario 3, I am changing over from distillate to heavy fuel oil using the generator to burn fuel out of the system. As you're changing over, what you're worried about is that if you change the temperature going through the high pressure pumps too quickly, you can seize the pumps. Now, Burmeister Wain on the present engine, it says 1 degree per minute. 1 degree per minute. So typically, we're going to start out somewhere at about 60 C, and I'm going to go up to about 120 C. It would take you about an hour to switch over. Now, when I start this system up, what you're going to see is initially when I'm going to switch over to distillate, I'm going to start up the supply pumps. You'll see the meters start to move to charge this system with fuel. But once the system is charged with fuel, you'll see no flow through the meter at all, and all of the fuel just circulating here. Then I'm going to start up a circ pump, go through a heater, go through the back flushing, right, and I'm going to be going like this. And you'll see that when you look at this, the flow rate here and here will match. And there'll be no flow rate here. Okay? So I'm circulating that fuel. Now if it is distillate, I know with the distillate on the simulator that I can preheat it to 60 degrees C. Okay? So what I typically do is, and within that, I will have you turn on the steam, right? And your steam tracing should be on. And I'm going to take and I'm going to leave it in manual. And then I'm going to put the heat on it and heat up the fuel that's in the circulating system. So I'm typically looking here, to 60 degrees C. I know I can do that without getting it, without having a problem with the fuel that we're using. But I can only heat it very quickly because the generator is not burning heavy. It is on distillate. So I'm not worried about unequally expansion of the plunger to the barrel causing it to seize. And then I'm going to let it circulate through this system. I'm going to let it circulate through this system, right, and to the generator and back for at least, typically in real life, I would do it in 30 minutes to make sure that the pump plungers are equalized on the generator. But anyway, I'm going to let that circulate for a while. And then when I start the generator up, now after the generator starts, you will see these meters are moving, but they will be exactly the same. Once I start the generator, this number is going to be higher than this one. So what's going on, the difference between how much fuel I'm delivering and how much is coming back is how much you burned, and you will see the flow coming in. Now I'm pulling distillate in. When I'm just going in a circle, I'm not pulling distillate in. And what I'm trying to do is get the viscosity down here so that and again on distillate, I don't care if it's down this low, as long as it's above 2 centistones. So that as I burn that heavy fuel oil away, it's going to slowly, and pull in heavy, it's going to slowly come up. And then once I start the generator, I'm going to put the changeover computer on. And the changeover computer, what it's doing is it is going to change the set point of the temperature controller at 1 degree per minute. So I'm slowly increasing the heat, and I'm burning distillate out of the system and replacing it with heavy. But what you'll find, even with just doing the generator, this is slowly going to come up. And if it starts getting into the too viscous, then I can always put some distillate back in. And I can put as much distillate as I want. I can do it in shots, or I can do it slowly. It doesn't really matter. So what am I doing? I'm controlling, I am slowly pulling the heavy into the system. I am changing the temperature at 1 degree per minute, and I'm adjusting the mixing of distillate in or heavy in to maintain this system viscosity and range. All right, that pretty much concludes this discussion. I hope it has been helpful to you. Thank you very much.